Namaskar friends. From last lecture we are learning the third chapter, that is viscosity and surface tension. In viscosity we have discussed about the types of flows, that is a streamline flow and turbulent flow, laminar flow. In this way, basic things of viscosity you have already discussed in 11th and 12th. See friends, the viscous liquid, when it having a motion, at that time it having a energy. And see friends, it having three types of energy, that is kinetic energy, potential energy and pressure energy. We have discussed these three types of energies in last lecture. Today we will see the Bernoulli's theorem, what he says in that theorem. We have to discuss with the diagram and we have to derive the relation of the Bernoulli's theorem. See, you are here able to see this diagram. This figure itself represents a tube. In this tube, a flow of liquid between two transverse sections. This transverse section is P and this transverse section is Q. See, let the pressure, velocity and cross-sectional area of this tube, we will denote it at this P. The P1 is the pressure, V1 is the velocity of liquid which is flowing through this end, and A1 is nothing but the area at this P, cross-sectional area. The corresponding quantities at the point this Q is denoted by P2, then V2 and A2 respectively. See, we will consider this distance is AB here, and the height H1 and here is a H2. Let us consider the steady flow. At the entrance of a small amount, here it enters a small amount of mass of the liquid through the section P, and the simultaneous exit of the same amount of mass M of the liquid through the section Q. In this journey of this liquid, we can say there is a loss of potential energy of liquid. How much quantity? Then we know that the formula for the potential energy equal to mgh, and therefore here loss of potential energy of liquid equals to mg. H is here difference between H1 and H2, that is nothing but H1 minus H2. But we know that the rho, density equals to mass upon volume, m by v, and that is nothing but m equals to rho into v. See here, don't confuse in the notation that it is it has been taken at capital, and here it is also same. it should be a capital, but due to a typographical mistake, this is a small. But keep in mind this V and this V is the same, and therefore loss of potential energy of liquid, that is this we will put the value of m, that is a rho into V. This is a rho into V, G as it is, and H1 minus H2 is as it is, and this equation we will denote it as 1. See now, force acting on liquid column. Yes, force acting on the liquid column. We are aware that force equal to pressure into area. Here, but we know that the work done equals to F into dl, and as V equal to here A into dl, and therefore if we are putting this dw, that is the work done, equal to what is the F into dl, and therefore F equal to dl as V equal to A into dl, this A into dl as E, and this F is equal to pressure, and this quantity is nothing but P, and A into dl equals to V, and therefore see, force acting on liquid column at section AB. At section AB, what is the quantity of force acting? That is F equals to P1 A1, and therefore we have to calculate the net amount of work done on the liquid in moving it through a distance dl. Through a distance dl, what is the net amount of work done on the liquid? Therefore, W equals to W1 minus W2. And see here, W1. What is the W1? W1 is nothing but P1V. And by subtracting the quantity P2V from P1V, here we will get, we will take it a common V, and P1 minus P2. We will denote this equation as number 2. See now, this work is obviously done at the expense of the pressure, energy of the liquid, and then represents a loss in the pressure energy of the liquid. Therefore, here total loss in energy of the liquid is given by equation 1 and 2. See now, this equation 1 represents loss of potential energy of liquid, and equation 2 represents the net amount of work done on the liquid in moving it through a distance dl. Therefore, now we will see what to do. Here, total loss in energy. Total loss, therefore, rho V into G. Again, I will you one thing that this V and this V is the same one. This is a rho Vg, H1 minus H2 plus V in bracket P1 minus P2. As this V, we will take it common, and rho into rho and this G here. Here H1 minus H2 plus here plus P1 minus P2. See, this is nothing but the equation number 3. See friends, Since the velocity v2 is greater than v1, means the liquid flowing from the tube having a velocity at v2 is greater than v1, and therefore due to which we having gain in kinetic energy of the liquid. See, for deriving the gain in the kinetic energy of the liquid, we know the equation for the kinetic energy, that is nothing but the 1 half mv square. Therefore here 1 half m is as it is, and v square means v2 square minus v1 square. See, keep it mind that rho equal to m by v. We know this, and therefore m equals to rho into v, and therefore by putting the value of m in this terms of rho into v, therefore we will substitute the gain in kinetic energy of the liquid equals to half into rho into v in bracket v2 square minus v1 square. This equation we will do it as in fourth number. Then we know that the law of conservation of energy, it says that the total loss in energy equals to total gain in energy. And if this statement we are writing in the equation form, that is v, then rho g in bracket h1 minus h2 plus p, means this equation number 3. We will compare this equation with equation number 4, half rho v into v2 square minus v1 square, and by solving this equation, see now rho, this one thing again I will give you remember this v is the same as this v, and therefore this v cancels here, this v also cancels. The remaining things are rho g h1 plus see this plus p1, then plus half rho v, this half rho v1 square, because if it comes to this side, it takes a positive sign. Then again rho g h2 plus C plus p2, because this p2 having negative sign, but when it comes to this side, right side, at that time it will be a positive quantity, then again it will be positive plus here half rho and this v2 square as it is. For simplification or for our required form of the equation, we will divide this equation by rho, and by dividing this equation by rho, then here gh1, because the rho will get cancelled, p1 by rho plus half, this again rho will cancel, p1 square equals to gh2 plus p2 by rho plus half v2 square. And see now by collecting the terms, and here gh plus p upon rho plus half v square equals to constant, and therefore this equation was established by the scientist Bernoulli, and therefore after his name is given for this equation, Bernoulli's equation for the viscous nature of the liquid, and this is the equation. See friends, this equation is asked number of times for the university examination for deriving it in the question of viscosity, and therefore keep in mind and remember these things about the Bernoulli's theorem. Try to solve whenever the question is asked to solve or to derive the Bernoulli's theorem, to derive the Bernoulli's equation. You have to come up to this, and by this way you will able to solve this Bernoulli's equation. Thank you very much.